This section is entitled Mathematical Induction, and the idea behind it is to prove something, to prove that one side, which equals another side, is true. We're going to be using a few things that we want to remember, which is just some of the summation formulas. So make sure that you have this handy, this sum of powers that we see over here, because those are things that we're going to need to know. The idea behind mathematical induction is fairly simple. To prove that something is true for all natural numbers n, we need to satisfy two things. First, we need to show that it's true for 1 when n is 1. And then we need to show that if it's true for all k, natural number k, then it is true for all k plus 1. So we're trying to show if it's true for this value, whatever that value is, it's also true for the next value, whatever that value is. And of course, we'll take a look at some examples. So this is actually us proving the thing that we see on one of the sums of powers formulas that we see on the last slide, but it's a good one just to show what mathematical induction is about. So remember, there's only two things that we need to show, and the first one is simply that what happens when n equals 1. So notice we're trying to prove that 1 plus 2 plus every other number up till some number n is the same as if you put that number in, multiply it by that number plus 1, and divide by 2. So just as an example, I just want to show you, just so that you're with me here, if we let n equal 4, for example, we'd be adding 1 plus 2 plus 3 plus 4. And what this tells us is that that should be equal to 4 times 5, so 4 times 4 plus 1 divided by 2. And we can see that the left-hand side is 1 plus 2 plus 3, which is 6, plus 4, which is 10. And then on the right-hand side, we have 4 times 5, which is 20, divided by 2, and that is also 10. So it's true for n equals 4, but we're trying to show that it's true for every value of n that we could possibly think of. So back to the first thing we need to show, it's just we need to show that it's true when n equals 1. So on the left-hand side, we just have 1. And then on the right-hand side, we put in 1 where we see n. So 1 times 1 plus 1 over 2, which, as you can see, is 2 times 1 over 2, which is just 1. So this is satisfied for n equals 1, and that is the first step in mathematical induction. So the second step is to assume that this is true for some value, and we're going to call that value k. And all we're going to do is put in k instead of n. This is an arbitrary number, it's just k, it could be anything. But we're going to assume that this is true. So we're actually assuming the thing that is true that we want to show is true. And then we are going to show that it's true. Our job is to show that it's true for what happens when you put in k plus 1. So that's just the next value. Whatever k is, we don't know. But if we can show that it's true for k plus 1, then we've shown that it's true that the original, what we're trying to show, is true by mathematical induction. So now we assume that it's true for some value k, and then, yeah, so we assume that this is true. Okay. Then for k plus 1, what we do is we just add the next term on the left-hand side. So the next term after k is a k plus 1. On the right-hand side, we do the same thing. So instead of k, we have k plus 1. Instead of k plus 1, we have k plus 1 plus 1. And so now this would be the next term in the series. Everything with k, we have added 1. We haven't taken anything away. We've just added 1 on the left-hand side, the k plus 1, to the left-hand side. And now we simplify and we try to make it so that the left-hand side equals the right-hand side. And the key with this, the key, is to really think about what we already assumed. So if you think about what you've already assumed, we assumed this thing right here. We assumed it in my line that is labeled by 2. We said that this thing here is equal to what we have above. So that is really the whole point here, is that we have said that that thing is equal to this thing. So now we can rewrite that piece as this. And that is the key. So I'm going to change that to what we assumed is true, that that is k times k plus 1 over 2 plus k plus 1. And we're trying to show that that's equal to k plus 1 times k plus 2 over 2. So now we just manipulate the left-hand side. We think about what we can do to it to try and, help us out here. And when you see fractions, a really good idea is to combine the two fractions. So we have a denominator of 2, and that's it. So if we give both of our other term a denominator of and numerator of 2, then we can add these two things together. So notice when we do that, a couple different ways to look at it, but we will have k times k plus 1 plus 2 times k plus 1 over 2. And we are still trying to show that that is k plus 1 times k plus 2 over 2. And what you should hopefully notice, and there's, like I said, you could have multiplied this all out. You would have had a trinomial. So if you're thinking, I know I would have multiplied that out, that's okay. It would have been a trinomial, and then you should have seen that you could have factored from there. So what I'm going to see is I have two terms, and they both share a common factor of k plus 1. So I can factor out my k plus 1 from both terms. That's what I'm going to do. So I'm factoring out a k plus 1. It's getting multiplied by a k plus 2. That's what I have left, and that's over 2. And then lo and behold, that's exactly what we have on the right-hand side. And so we have shown that the left-hand side equals the right-hand side. And because we have done that, we can now say that this formula holds for all n. Well, I'll be a little more specific. All natural numbers, there we go, by mathematical induction. And then we are done. So here's another example. Looks a little bit different, but it's the same idea. Use mathematical induction to prove that 2 is a factor of n squared plus 5n for all positive integers n. It's a little bit different. However, we can do this using mathematical induction. Same thing. We just want to start out with saying, what happens if we put in 1? So if n equals 1, then we have 1 squared plus 5 times 1, and that is 6. And we know that 6 is 2 times 3, which tells us that 2 is a factor of 6 and proves just that n equals 1 works. So we have that. Now, the next thing is the second piece, we're going to assume that 2 is a factor of k squared plus 5k. We're assuming that. Okay. And then what we want to do is show that 2 is a factor of, and then the next term, k plus 1, 5 times k plus 1. So what this does is it tells us, if we can show that it's true for k plus 1, the idea is k and k plus 1 are arbitrary. They could be anything. So we're doing a proving because we're showing that it would work for any k and k plus 1, but they could be any value we want. So therefore, then it's true for all our natural numbers. So we have this. And we just want to show that 2 is a factor of this. So a couple things that we need to do. We're going to multiply it out and combine like terms. You're welcome to pause if you want to do that, and then come back once you've done that. We'll have k squared, 2k plus 1 plus 5k plus 5. Now this is where that assumption that we made, that 2 is a factor of k squared plus 5k, comes into play. Because what we need to do is separate those things out. We assumed that 2 is a factor of k squared plus 5k. Because of that, I'm going to put those two things together. So k squared plus 5k, we assumed 2 was a factor of this. Then we'll write out what we have left, which is 2k plus 6. And what you should hopefully notice is that when we think about 2k plus 6, we notice that 2 is a factor of that, and we can factor it out. So we have our assumption where we said 2 is a factor. And then as we can see here, from what we wrote out, 2 is a factor here as well, because that 2 got factored out of that binomial. So if 2 is a factor of both of these things, then 2 is a factor of the whole thing, which is what we were trying to show. Okay. So now that we have that, we can now say that 2 is a factor of n squared plus 5n for all positive integers n. So notice a couple different ways we can say that. I'm actually going to add by mathematical induction. The reason I say that is because there are different ways to prove things, and we happen to be proving it using induction. So I should put that. And I mean, I'm sure I could write this nicer. Of course, I'd have to have better handwriting for that. So might not happen. And that's it. That's all we really have to show here. Showed that it was true for n equals 1, assumed it was true for this idea of k, any positive integer, same as the natural numbers. And then it's a factor of now this k plus 1. And so this is the second example here of mathematical induction complete.